A useful sufficient criteria is convexity. First, let's revisit hyperplanes. Given any 3 points in any finite dimensional space, those 3 points define a 2-dimensional plane. Since it's 2 dimensions, I'm right back to Calc 3, and the inner product is equivalent to length A, length B, cosine theta, giving us our 3 criteria for inner products: positive, 0, and negative. 0, the vectors are orthogonal. Positive, acute angle, and negative, obtuse angle. With this in mind, let's redefine a hyperplane. Hyperplane goes through a point and has a given normal. I take all the points where the vector that connects is orthogonal to n. Those points define the hyperplane. To align it with the notation from before, the fixed point, the point that's varying, and the normal. We'll scale the last component to be -1, so only normals that are non-vertical are allowed for this definition. And then it's just a matter of re-expanding to get the definition from before. One more thing to define: half spaces. Given a hyperplane going through a given point with a given normal, the hyperplane divides space into 3 pieces: the half space below the hyperplane, and the half space above the hyperplane. And the shared boundary for both half spaces, the hyperplane itself. The supporting hyperplane theorem now is what we'll be proving. Given a closed convex set and a point on the boundary of that set, there exists a hyperplane that goes through that point so that S lies below the hyperplane. This hyperplane is then a supporting hyperplane. The proof requires a little bit of analysis, which I know you don't have, but it shouldn't be too bad. Take a sequence of points outside the set, converging to x0. For every x sub k, take its projection onto the set S. Projection, remember, is the minimum distance to the set. We'll define a sequence of normal vectors of unit length. Infinite sequence of vectors, a finite dimensional set, convergent subsequence. Because S is convex, it's a quick calculus argument to show that this inner product must be negative. All that remains is a quick bounding argument and passing to limits. This term adds 0 cleverly. And notice that this first term is exactly the length of that normal vector. Removing that negative number gives us an inequality. With our bound now in terms of our sequence that we know converges, passing to the subsequence and drive k to infinity. The normal vectors converge, and the sequence converges. But this is exactly the estimate we need to show that S lies in the half space below the hyperplane.